So, welcome to another lecture on the subject AAT. We will be continuing with module number 3. So, in this lecture, we are going to look at oblique incidence for perpendicular polarization. So, in the last class we have seen parallel polarization, where we told that parallel polarization means the electric field is in the same plane as that of the plane of incidence. For a perpendicular polarization, the electric field is perpendicular to the plane of incidence. Let us look at it using a diagram. So, let us say I have the boundary, which is the x axis. There is this z axis. The light is incident at an angle. It gets reflected. It will also get transmitted. So, the propagation vector for incident light is ki, the propagation vector for transmitted light is kt, and the propagation vector for the reflected light is kr. Let theta I be the angle of incidence, theta r be the angle of reflection, and theta t be the angle of transmission. We have another axis which is y, which is directed towards u. So, basically you have the boundaries is something like this. So, boundary like this, and the light is incident on this boundary, and y is towards u, it is pointing towards you. Okay. Now, the first one, this is median number 1. Where you have mu 1, epsilon 1, beta 1, eta 1, etc. This is medium number 2. Mu 2, epsilon 2, beta 2, eta 2, etc. Now, we say that the plane of incidence is this, that we have already stated. The plane in which the light is propagating is the plane of incidence. So, this is our plane, which is our xz plane is the plane of incidence. So, in this case, this is xz. Now, for perpendicular polarization, the electric field is perpendicular to the plane of incidence. So, the electric field here, for example, for the reflected wave will be along y direction pointing towards you. For incident wave also along y direction pointing towards you. For reflected wave also, let us assume that the electric field is in y direction pointing towards you. So, since now the propagation and the electric field is perpendicular, the magnetic field should also be perpendicular to both of them. So, the magnetic field will be something like this, HI. Similarly, for reflected wave, it will be something like this, HR. Similarly, for transmitted wave, it will be something like this, HT. Now, you can see that the magnetic field, the electric field, and the direction of propagation all are perpendicular to each other. And you see that the wave is incident at the plane where Z equal to 0. So, this plane has the value of Z equal to 0. Now, let us write the equations. You see electric field E, let me mark the field, this is EI, this is ER, and this is ET. So, in medium 1, for incident wave, EIS is equal to, the electric field is parallel to y axis. So, you do not want to resolve it into any components. You see that the electric field is pointing towards you, the y axis is also pointing towards you. That means, the electric field can be written in terms of the unit vector along y. So, EIS, I can write it as the magnitude EIO into e raised to minus j Ki dot r, where r is the unit vector x ax cap plus y ay cap plus z az cap, and Ki has the magnitude is equal to beta 1, because it is in the first medium whose beta value is beta 1. But Ki is at an oblique angle, it is not parallel to x, y or z. So, we need to resolve the Ki into parallel components along each of the axes. So, let us do how we can do that. So, Ki is something like this. Okay. So, I can draw the two perpendicular components as one parallel to z axis and one parallel to x axis. So, this is Ki, this is Ki z, and this is Ki x. Now, you see that both Ki x and Ki z, or you can say Ki z is parallel and in the same positive direction of that of z. Ki x is parallel to x and is in the positive direction of x. Okay. And the angle which makes is, so this is theta I. Okay. So, I can write Ki as the magnitude beta 1 multiplied by sine the theta I is actually here. So, Ki z is adjacent to theta I. So, the Ki z will have the value cos theta I az cap, and Kx is opposite to that of theta I. So, Kix will have value sin theta I ax cap. So, I can write the complete Ki as beta 1 into sin theta I Ax cap plus cos theta I Az cap. Okay. So, your Ki dot r is equal to beta 1 x sin theta I plus z cos theta I. Okay. So, you can substitute that in EIS. So, it will be EIS is equal to EI0 e raised to minus j beta 1 x sin theta I plus z cos theta I. This is very simple because EI is along y direction, but HI is slightly different. We need to resolve HI. So, HIS is equal to, I have HI0 multiplied by, you see HI is in this direction. Okay. So, I can resolve this into two components, one along negative x and one along positive z. So, this is HI, this is HIX and this is HIZ. And the angle theta I will be here. So, the value of HIX has minus cos theta I Ax cap and HIZ is equal to sin theta I Az cap. Why there is a minus in HIX? Because it is in the opposite direction or it is along the negative x axis. X axis, the opposite direction is this direction, but HIX is in this direction. And HIX is adjacent to theta I, because of which we will have cos theta I. And HIZ is in this direction and your Z is also in this direction. And HIZ is in the opposite side of cos theta I, because of it you have sin theta I. So, I can write HIS is equal to HI0 minus cos theta I Ax cap plus sin theta I Az cap multiplied by, the exponential term will be same for both electric and magnetic field for a particular wave. So, this will be is equal to minus j beta 1 into x sin theta I plus z cos theta I. Now, HI0 I can write in terms of EI0, this is equal to EI0 by the intrinsic impedance of first medium, that is eta 1 into minus cos theta I Ax cap plus sin theta I Az cap into e raised to minus j beta 1 into x sin theta I plus z cos theta I. Okay. So, we have found out for the incident wave what is the expression for the electric and the magnetic field. Now, let us look at the expression for the reflected wave. So, when you consider the reflected wave, let us look at Kr. So, Kr is in this direction, which I can resolve into two components, one along x which is positive and one along z which is negative. So, this is Kr this is KRX and this is KRZ. You see KRX is along the positive x direction, KRZ is along the negative z direction. Okay. So, and the angle theta r is at here. Theta r. Now I can write KRX as, it is opposite to that of theta r. So, this is, and this is positive direction, sin theta r AX cap. And KRZ is along minus z direction, so there is minus, and it is along the side which is near to theta r. This is minus cos theta r A Z cap. Okay. So, I can write my ERS is equal to ER0, which is a magnitude, e raised to minus j kr dot r, where kr is equal to the magnitude which is beta 2 into the sum of KRSZ and KRX. So, that is sin theta r AX cap minus cos theta r AZ cap. So, I can write ERS is equal to ER0 e raised to minus j beta 2 into r is our position vector, which is already mentioned here, x AX cap plus y AY cap plus AZ cap. So, when you do a dot product with KR, you will get x sin theta r minus z cos theta r. Similarly, and this is along y direction. I think I have forgot to mention the direction in the previous case. This is along y direction. And HRS will be equal to HR0 multiplied by, you see the HR here is in oblique direction. We need to resolve into two parallel components parallel to each of the axis. So, HR is something like this. This is HR. So, I can resolve into one component parallel to z axis and other component parallel to x axis. So, this is HRZ, this is HRX. And the angle is theta r here. So, HRX is adjacent to theta r. So, that will be sin theta r AX cap and is in positive direction of x. HRZ is also in the positive direction of z, but it is in the opposite side. I am sorry. This will be, since the HRX is near to theta r, it will be cos theta r AX cap, and HRZ will be opposite to that of theta r, it will be sin theta r of A Z cap. Both are positive because both are in the positive x and positive z direction. So, your HIS is equal to HR0 multiplied by the sum of HRZ and HRX. So, that will be cos theta r x cap plus sin theta r a z cap into e raised to minus j beta 2 into x sin theta r minus z cos theta r, which I can write as ER0 by the intrinsic impedance of first medium into cos theta r x cap plus sin theta r ay cap, sorry, az cap into e raised to minus j beta 2 into x sin theta r minus z cos theta r. So, this is in medium 1. Let us go to medium 2. In medium 2, you have the transmitted wave. For the transmitted wave, again E t is parallel to y, so it is in a y direction, but k, the propagation vector, is in some arbitrary direction. So, you need to resolve k t along the direction of the axis. So, this is k t, which I can resolve into two components, one parallel to z and other parallel to x. So, this is k t x and this is k t z. And the angle, as you can see from the figure, it is, this is theta t. So, k t z is adjacent to the angle. So, the value here will be cos theta t a z cap, and it is in positive direction of z. So, it will be positive. K t x is in positive direction of x, but it is in the opposite side of the angle. So, it will be sin theta t a x cap. So, my value of E t s is equal to E t 0 into e raised to minus j k t dot r along the direction of y, where k t has the magnitude is equal to beta 2 because it is in the second medium. So, your final value of k t vector is equal to the magnitude beta 2 multiplied by the sum of k t z and k t x. So, that is equal to beta 2 multiplied by sin theta t x cap plus cos theta t a z cap. So, I can write where r is again the same position vector. So, I can write E t s is equal to E t 0 e raised to minus j beta 2 into x sin theta t plus z cos theta t into a y cap, because the electric field is in y direction. Now, H t s is equal to H t 0 multiplied by H is in some arbitrary direction. So, you need to resolve it again. So, this is the direction of H. So, you resolve into two components, one negative of x and one positive of z. So, this is H t, this is H t x and this is H t z. And the angle is this theta t. So, I can write H t x as H t x is in the negative direction of x, so there will be minus, and it is adjacent to theta t, so there will be cos theta t Ax cap. Similarly, h t z is in the positive direction of z, but is opposite to the angle. So, that is sin theta t A z cap. So, I can write ht0 as sum of htx and htz. So, that is equal to minus cos theta t Ax cap plus sin theta t Az cap multiplied by the same vector e raised to minus j beta 2 into x sin theta t plus z cos theta t, which again I can write as ht0 by eta 2, because in the second medium, sorry, this is et0 multiplied by minus cos theta t Ax cap plus sin theta t Az cap into e raised to minus j beta 2 into x sin theta t plus z cos theta t. So, we have found out expressions for electric and magnetic fields in all the different waves. Now, we will apply the boundary condition. Which says the magnitude of electric field, the tangential component of electric field in medium 1 should be equal to the magnitude of tangential component of electric field in medium 2. Now, remember, we are assuming that this is a source free medium. So, that is why the tangential components are same. If it has some source, the difference of the tangential component will be equal to rho v. So, this again for the magnetic tangential component of magnetic field in the first medium should be equal to the magnitude of the magnetic component of the tangential component of magnetic field in the second medium. Okay. Now, what is a tangential component here? You see, for E is tangential to the surface, to the boundary, because E is along the y direction. So, this is your boundary, and E is along this direction, which is y, or in this direction, which is y. So, it is tangential. So, the y direction is tangential to the boundary. Okay. Similarly, for H, it has two components along z and x. So, this is the boundary and x is something like this, which is tangential to the boundary, but z is something like this, which is perpendicular to the boundary. So, the tangential, all the components of x and y are tangential to the boundary. I will write that also. The components of E and H along Ax cap, which is x direction, and Ay cap are tangential to the boundary. Okay. So, and we evaluate the tangential component at z equal to 0. Why? Because the boundary is at z equal to 0. Okay. So, in medium 1, the magnitude of electric field tangential component, I can write this as the x component of the complete component of EI0, which is this. Now, you see the magnitude of this is equal to 1. Because it is a complex exponential type, the magnitude will be 1. So, it will be EI0 plus ER0. Why? Because for ER0 also, you see you have ERS also, you have ER0, and there is an exponential component whose magnitude is equal to 1. So, that is the total transition component of electric field in the first medium. Now, what about the tangential component of magnetic field in the first medium? So, let us look at that. So, for the incident wave, you have this part which is tangential, this is perpendicular or normal, which we want to take, and you evaluate at z equal to 0, or you can say the magnitude of this has equal to 1. So, when you take the magnitude, you will end up only with this part. Okay. So, I can write H tangential 1 along 1 is EI0 by eta 1 into minus cos theta I plus, there is a reflected wave whose tangential component for magnetic field is this. So, this is perpendicular, this part, and this has magnitude equal to 1. So, I do not want to take all these terms, I can take only this part. So, this I can write as plus ER0 by eta 1 into cos theta I. Let us look at medium 2. The magnitude of electric field tangential component in medium 2 is equal to, you see that the tangential component is this term, because this has magnitude equal to 1. Okay. So, this is equal to ET0, and the tangential component of the magnetic field in medium 2 is equal to, you see that this is the tangential component because it is along x, this is perpendicular component, and this has magnitude equal to 1, because of which I can take only the first term. So, I will take this as ET0 by eta 2 into minus cos theta t. Okay. Now, let us combine all of them. So, what we say that the electric field tangential component in medium 1 will be equal to the electric field tangential component in medium 2. So, I can write implies applying boundary conditions EI0 plus ER0 is equal to ET0, that is from this and this. So, let us say that, let me number this as equation number 1, and EI0 or minus EI0 eta 1 cos theta I plus ER0 by eta 1 cos theta I is equal to minus Et0 by eta 2 cos theta t. Let equation number 2. So, I am just multiplying equation number 2 with minus sign. So, I can write this as EI0, or in more general term I can write 1 by eta 1 multiplied by EI0 minus ER0 into cos theta I is equal to 1 by eta 2 Et0 cos theta t. I just multiplied with minus. So, let us say this is equation number 2, same equation, or let me take as equation number 3. Fine. Now, we want to find a relationship, just like we have did for parallel polarization. We want to find a relationship between EI0 and ER0, also EI0 and ET0. Okay. So, let us do the manipulations. From 3, I just going to cross multiply eta 1 to the right hand side. I am going to move cos theta I also to the right hand side. So, which means I have EI0 minus ER0 is equal to eta 1 by eta 2 Et0 cos theta t by cos theta I. Let this be equation number 4. And from equation number 1, you have EI0 plus ER0 is equal to ET0. So, let us add 1 and 4, implies 2 EI0 is equal to eta 1 cos theta t by eta 2 cos theta I into Et0 plus Et0. So, this is Et0 multiplied by 1 plus eta 1 cos theta t by eta 2 cos theta I. So, this is equal to Et0 multiplied by eta 2 cos theta I plus eta 1 cos theta t divided by eta 2 cos theta I. Implies I can write Et0 by EI0 as 2 eta 2 cos theta I by eta 2 cos theta I plus eta 1 cos theta t. And this is called as the transmission coefficient for perpendicular polarization. Okay. So, for perpendicular polarization, this is called as the transmission coefficient. Fine. So, basically we have found a relation between EI0 and ET0. Now, let us try to find a relation between EI0 and ER0. Okay. So, you can write from 3, I am going to move this here and move this here. Okay. So, I can write this as eta 2 by eta 1 multiplied by EI0 minus ER0 into cos theta I by cos theta t is equal to ET0. Let this be equation number 5. And from 1 you have EI0 plus ER0 is equal to ET0. Now, you see the right hand side of both the equations are same. RHS is same. Implies I can write, you can equate both the equations as eta 2 by eta 1 into EI0 minus ER0 into cos theta I by cos theta t is equal to EI0 plus ER0. Now, let us group the terms of EI0 and ER0 separately. So, grouping the terms of EI0 and ER0 separately, we get, I can write eta 2 by eta 1 EI0 into cos theta I by cos theta t minus eta 2 by eta 1 ER0 cos theta I by cos theta t is equal to EI0 plus ER0. Now, let us bring this ERI0 to the left and this ER0 terms to the right. So, I can write EI0 multiplied by eta 2 cos theta I by eta 1 cos theta t minus 1 is equal to ER0 into 1 plus eta 2 cos theta I by eta 1 cos theta t. So, this is EI0 into eta 2 cos theta I minus eta 1 cos theta t divided by eta 1 cos theta t is equal to ER0 into eta 1 cos theta t plus eta 2 cos theta I divided by eta 1 cos theta t. So, you can cancel eta 1 cos theta t in both sides. So, you will get the ratio of ER0 by EI0 is equal to eta 2 cos theta I minus eta 1 cos theta t divided by eta 1 cos theta t plus eta 2 cos theta I. And this is called as the reflection coefficient for perpendicular polarization, which relates the magnitudes of electric field of reflected and incident wave. So, this is the reflection coefficient of perpendicular polarized wave. This is similar to that of the expression that we had derived for parallel polarization, but there are some subtle changes. You can analyze and find out what are the changes. Also, you can prove that 1 plus tau reflection coefficient is equal to the transmission coefficient. So, you can write as a homework to prove this. Also, the reflection coefficient is equal to 0 when eta 2 cos theta I minus eta 1 cos theta t is equal to 0, or eta 2 cos theta I is equal to eta 1 cos theta t. Fine. Let us square this. Eta 2 square cos square theta I is equal to eta 1 square cos square theta t. Now, the condition at which this satisfies, where the reflection coefficient is 0, is the condition in which all the incident wave is transmitted. And the angle at which this is incident is called as Brewster's angle. This we have already seen, which is equal to theta b perpendicular. Okay. So, this theta I can write as eta square into 1 minus sin square. Instead of theta I am writing it as theta per b is equal to eta 1 square into 1 minus sin square theta t. Now, you can substitute the values of eta and etc. So, you will find that the value of sin square theta b Brewster's is equal to 1 minus mu 1 epsilon 2 divided by mu 2 epsilon 1 divided by 1 minus mu 1 by mu 2 whole square. The square of sine of Brewster's angle is equal to 1 minus mu 1 epsilon 2 by mu 2 epsilon 1 by 1 minus mu 1 by mu 2. Now, for non-magnetic medium, mu 1 equal to mu 2 equal to mu 0 implies 1 minus mu 1 by mu 2 is equal to 0, implies your sin square theta Brewster will tend to infinity, which is not possible, because implies your sin square theta sin theta Brewster is infinity, implies the value of sine is infinity. Because it is not possible. Why? Because but the maximum value of sine is 1, implies not possible. So, for a non-magnetic medium, you will not be able to find a Brewster's angle. Also, if mu 1 is not equal to mu 2, but epsilon 1 is equal to epsilon 2, implies I can write my sine of theta b perpendicular is equal to root over mu 2 by mu 1 plus mu 2. You can just substitute this in this equation, you will get the value. Okay. So, this is the oblique incidence of a perpendicular polarized light. I hope you have understood this. Let me know if you have any questions. Thank you.